Hey guys, and welcome to another video in my series of videos about thermodynamics. In this video, we are going to start the higher level thermodynamics, the university level thermodynamics that I've decided to do some videos on. So none of this stuff is going to be in the A-level syllabus. It's all going to be sort of higher level, university level oriented physics. So basically what I'm going to try and cover in this video is the zeroth and first law of thermodynamics. There's quite a bit to cover in each one. But before I start that, I'm just going to go into a few little details about, like, some of the mathematics and some of the terminology that I'm going to be using in this series. So let's get started. I firstly want to define what I mean by these two terms right here. So we've got the word macroscopic and microscopic. Now you might already be familiar with these terms. Macroscopic's probably got to mean something to do with big, microscopic something small. But in thermodynamics, we talk about these macroscopic quantities like temperature, pressure, volume, the stuff that we were sort of talking about quite a bit in the last video. But we also have things like microscopic quantities, which are sort of like speed, sort of mass, stuff that's associated with the very, very small. Thermodynamics is kind of about unifying these two together with mathematics, and that's kind of what's so nice about the subject, is that it kind of ties in these two. And lots of famous scientists like Boltzmann and Gibbs and Maxwell did a lot to kind of unify that. That's kind of what we're saying when we talk about macroscopic and microscopic quantities. The next thing I want to go over are the different types of change in thermodynamics. So there's a few sort of terms that you need to be quite familiar with when we talk about types of change. So what do I mean by types of change? Well, let's say we have our gas. It may or may not be ideal this time, but we have our gas here, and these are all the particles in the gas, and of course they're all sort of moving around rapidly and randomly. And we're going to do some sort of a transformation on this gas. We're going to try and change this gas in some way. Now, there are several different ways in which we can change the state of the gas, and I'm just going to define what each of them are. So the first type of change that I'm going to introduce is isothermal. Now, if you remember Boyle's law stated that pressure is proportional to 1 over volume at constant temperature. And another word for constant temperature is isothermal. If you just look at the word, iso means at constant, and thermal, of course, means temperature. So isothermal basically means at constant temperature. So if you have an isothermal change, then the change happens at constant temperature. And Boyle's law applies for an ideal gas. So if you're doing an isothermal change on an ideal gas, then Boyle's law applies of pressure equals 1 over volume. Another type of change is isobaric. And baric basically just means at constant pressure. So which ideal gas law was at constant pressure? Well, it was actually Charles' law, which stated that the volume is proportional to the temperature. So for an ideal gas, remember this is only for an ideal gas we're talking about here, volume is proportional to temperature, which is Charles' law, but only for constant pressure, which is what isobaric means. And the other one, you can probably guess what it's going to be. It's isochoric. An isochoric change, you can probably guess the variable. It's going to be at constant volume. And the law which we talked about in the last video was the pressure law, where pressure is proportional to temperature, which is true, and this is the case for an ideal gas as well. So these gas laws we identified are only true for an ideal gas. However, you can have isothermal changes, isobaric changes, isochoric changes for any type of gas, whether it be an ideal gas or a real gas. They can all undergo these changes. But in the case that they are an ideal gas, then these three laws hold. But there is another type of change, and it's called an adiabatic change. You're probably thinking, well, what are we going to keep constant? We've kind of ran out of variables to choose from. But an adiabatic change is kind of defined a little bit differently. It just basically means that there is no change in heat energy. So no heat enters or leaves the system. So Q equals 0 for an adiabatic change. Now there is actually a thing which is constant for adiabatic, but we will find out what that is a little bit later on. So those are our different types of system. Just a few more things before we sort of get into thermodynamics properly. I want to just go over what the difference between state variables and process variables are. So I'm just going to draw a little column right here. So we have state variables and process variables. What do I mean by state variables? Well, say you have this gas right here. This gas is said to be in a certain state. So it's got a certain pressure, a certain temperature, a certain volume, and all of those variables, temperature, pressure, volume, you can probably have other things like number of moles or another thing called entropy, which is very important to thermodynamics. We'll get into that very, very soon. All of these are what's called state variables. They define the state of the gas. So let's just write out a few. So we've got temperature, volume, pressure, number of moles, number of molecules. You can have maybe another thing like density if you really wanted. But also this quantity called entropy, which we give the letter S. And I'm going to go into entropy very soon, don't worry. So these are all state variables. Also, another important one's internal energy. You can have one called enthalpy, which is another thing we'll get into. Well, enthalpy. Don't get confused between enthalpy and entropy. So those are all state variables of a system. So what are process variables then? Process variables are the variables which you use to describe the system as it's changing. Now, there aren't that many process variables, but say you add heat to a system. The heat that you add is kind of changing the gas as you add it. So a gas doesn't necessarily have a certain amount of heat at any one time, but you apply heat to it. So for this reason, we say that heat, Q, is in fact a process variable. At any one point, it doesn't really have any heat. Apply a certain amount of heat to the system in order to get it to change from one state to another. Another one is work, and that's another very important process variable. Work is the amount of work that you do to a gas, which is related to how the volume changes, and again we'll come on to that very soon. Another one is heat capacity. That's also a process variable similar to heat. But you can actually find that heat capacities are quite constant particularly for ideal gases. So these are all process variables. So that's the difference between state variables and process variables. And the last thing I just want to go over are what exact and inexact differentials are. I'm going to be using the notation that my university gave me for these. Yeah, so what is a differential? I'll just go into that first of all. What is a differential? Well, say you have your gas. Let's draw our little box of gas that we're familiar with, or hopefully familiar with. And say the gas expands slightly to fill a slightly bigger volume. And what we're going to do is we're going to imagine that this increase in volume is tiny. It's what's called infinitesimal. It's a arbitrarily small increase in volume. Well, we say that at first it has the volume V, but what's the new volume? Well, the new volume is going to be the old volume V, but we're going to add to it this tiny infinitesimal change, dV. This is what the little d does. D basically means infinitesimal. So if you see if you see a variable preceded by the lowercase d, that basically means that it's an infinitesimal change. So this gas has expanded from volume V to volume V plus dV right there. So that's the process that's just happened. And volume, we say, is an exact differential. In fact, all of these variables here are exact differentials. And what do I mean by exact differentials? Well, it's kind of quite a complicated calculus thing, but basically it means that it's what's called path independent. So it's like the way in which you get from volume, so let's say you've got two volumes, volume 1 and volume 2. Let's say you get there from here to here. It doesn't matter how you get there. The value will be the same if you get there using there or get there using there. The change in volume V2 minus V1 is the same. However, an inexact differential is one which is path dependent. So the way in which you get from one state to another is path dependent, and that's simply because of process variables. So let's draw out a graph. We're not going to put any axes on this graph quite yet. This is just an arbitrary graph right here, and there are just it's between two random variables. We don't know what they are yet, but there's going to be 2 points on this graph. We're going to have point 1 and point 2. So let's say our first route is this way. When we evaluate this route, like maybe using an integral or something, we're going to get a different value than if we go this way, if the differential is inexact. So basically this is kind of saying that this change here is putting in a different amount of heat than this change here, despite the fact that you get to the same position in the end. So heat, it's path dependent, and the way we represent this is simply with, rather than just an ordinary d, we use a curly d, and that means inexact differential. Now, typically we don't really like working with inexact differentials because they're a lot harder to integrate than exact ones. And in a couple of videos time we're going to get into more of the detail about exact and inexact differentials and how you can kind of convert between the two. But that is basically what an inexact, that basically means that the variable, the quantity of the variable depends on the path in which you took through that variable. So that is all of the basic knowledge that we're going to need for thermodynamics. So let's get right into it. So let's start by looking at the laws of thermodynamics. Now, there are actually 4 laws of thermodynamics, weirdly enough. There's the zeroth, first, second, and third laws of thermodynamics. You're probably wondering, why is there a zeroth law? Well, the reason is that the first 3 laws had already been formulated, but the first 3 laws all refer to temperature, but then somebody realised that nobody had defined temperature, and that is what the zeroth law is. So let's start with the zeroth law. It seems like a good place to start. The zeroth law of thermodynamics. It does sound a little bit weird, but yeah, that's history. So what is the zeroth law? Well, it's kind of what I was saying in the last video about temperature and how temperature kind of flows between various different objects, and it's very obvious, really, if you think about it. So let's say you have a body here, body A. So this is just any sort of system, just a body A there, and let's say you have another body B here and another body C here. Now, it's going to sound quite obvious, this, but if A and B are in equilibrium, and if A and C are in equilibrium, then it must follow that B and C are in equilibrium. Now, I know that sounds kind of quite obvious, but what do I mean by thermal equilibrium? Well, it's basically just a fancy way of saying they're at the same temperature. And so what the zeroth law is saying is that if you bring one body into thermal contact with another body, and then you bring another body into thermal contact with the first body, then it must follow that the same temperature. Heat has flowed in order so that the temperature is the same between the two bodies. And so all three bodies are at the same temperature. They're all in thermal equilibrium. And so that's kind of what we mean by temperature. It's a bit of a funny law, but they had to add it historically because no one had defined what temperature was. So that's the zeroth law, all there really is to it. And so now we're going to move on to the first law of thermodynamics. So, what is the first law of thermodynamics? Well, it's basically a statement about the conservation of energy of a system. It says that if there's a change in energy of a system, then that must mean either two things: that heat has been added to the system, or work has been done by the system. And so how can we express this mathematically? Well, we say that delta U, which is the change in internal energy of the system, we define what internal energy was. It's the total amount of kinetic energy in this gas, in this box of gas that we're talking about, is equal to Q, which is the heat added to the system, plus W, which is the work done on the system. So it's basically saying that heat and work are both equivalent in the sense that they change the internal energy of the system. And so that is the first law of thermodynamics, and it's very important, and it's often the starting point of many derivations which will follow. Now you're probably noticing that there's no deltas in front of Q and W. And that's because I've defined Q and W to be process variables, and so therefore they don't have a delta sign because you can't really sort of have change in something that's already changing. So Q is the heat added to the system, W is the work done on the system. And so that is the first law of thermodynamics. So I'm now just going to go through the sign conventions that I'm going to use. So I'm defining Q, positive Q, to be the heat absorbed by the system. So if heat is being absorbed by the system, then I'm going to define that as being positive heat. If heat is leaving the system, then there's negative heat. So that's how I'm going to define Q. I'm also going to define the work done to be, well, the positive work done to be the work absorbed by the system. So if the system is absorbing work, then W is positive. If the system is doing work on something else, then W is negative. So that is the two sign conventions that I'm going to do. So let's just think a little bit more about what work is. And to do that, we're going to draw off, probably quite familiar by now, a piston. We're going to draw a piston out, and this piston is going to be full of a gas. It doesn't have to be an ideal gas, it can be sort of any real gas. This will apply to any gas, and of course the molecules are moving around, bumping off the walls of the container, doing pretty much whatever they want. And we said before that the gas has a pressure P, a temperature T, and is occupying a volume V. However, the volume is now free to change. Unlike in a box of gas before, the volume was fixed. However, with this piston right here, the gas can actually sort of move the piston or the plunger up and down. And if it's moving it up, then obviously the gas is doing some sort of work on the system. But if you press down on this piston, then you're doing work on the gas. And so let's just kind of quantify this a little bit more. So what do we know about work? Well, we kind of know what it is classically, right? Well, classically, the work done is equal to the force multiplied by the distance in which the force does the work. So say if you apply 10 newtons through 2 meters, then you've done 10 times 2, which is 20 joules worth of work. So that is what the definition of work is. So let's say you move this plunger down a distance of delta x right here. So delta x is the change in the position. You can probably say that this is x2, this is x1, and delta x is the change in the position. It's x2 minus x1. But what is actually doing this work? Well, if we think about it, there's the pressure of this gas is what's doing the work. And what do we say pressure is? Pressure is simply force divided by area. And so therefore we can substitute in this formula that the force is the pressure multiplied by the area multiplied by delta x. But what is this quantity here, A delta x? Well, if we think about it, then delta x is the change in the position. Multiply that by the area in which the pressure is acting, which is this surface here. Well, we're going to get the volume. We're going to get the sort of the change in volume. We're going to imagine there's a sort of volume there that's kind of been moved through. And so therefore you end up with the work is the pressure multiplied by the change in volume. So A delta x becomes delta V. However, there is one small caveat. We defined that if the gas was doing work, then that would be a negative term for work. And so what is the direction in which the gas is doing work? Well, the gas would be doing work on it this way, which would cause the volume to increase, but that would result in W being negative, because that's not work being absorbed, that's work being done by the gas on the system. So what we're just going to have to add is we're now going to have to add just this minus sign right here, minus P delta V, and that just shows that the pressure the work is being done to compress the gas. Positive work is being done to make the volume smaller. And this is a very important relationship, W equals P delta V, and we're going to be using this a lot. You can also equivalently write it in its infinitesimal form. So what's that? Well, W, I said, was a process variable, so you're going to have a curly D. So dW equals minus P dV. So that's kind of the the volume work written as a differential. And similarly, you can also write the first law as a differential. You say that du equals dq plus dw. So I'll just highlight those again. So this is the differential, the infinitesimal differential form. It's going to be very useful when we're going to be integrating these terms. So I now just want to go over what is the work done for each of these different types of processes. So we're going to sort of take a little break and talk about work being done right here. So what is the work done on these four different types of processes? Now let's start with the simplest one, isochoric. What does isochoric mean? Constant volume. And so what's going to happen if we have constant volume? If we can't move this piston at all, if we imagine that we weld the piston in place, then what's going to happen? Well, this term right here, let me just write it out again. We're going to get that W equals minus P delta V. What's the change in volume? It's just going to be 0. So in an isochoric process, you're going to get no work being done. And that's a key thing to remember. If the process is isochoric, then W equals 0. And from that, you can go back to the first law and say that delta U is simply Q. And that says the only way to get a change in energy, internal energy of the gas, is to add heat. If it's isochoric, that must mean that this term, W, is 0. So that's isochoric. What about isobaric? What about an isobaric work done? Well, isobaric, so let's start with the same formula. W equals minus P delta V. So what's constant with an isobaric change? Well, the pressure is constant right here. So you don't need to do any integration because the pressure is constant, and so therefore you can just write minus P, the final volume VF minus the initial volume VI. You could also tidy that up if you really wanted to, if you don't like minus signs. So VI minus VF, that is the work being done in an isobaric process, and P is constant. But now let's move on to an isothermal change, which is slightly more complicated. The work being done isothermally is slightly more complicated. So what is the work done? Well, W equals minus P delta V. That is our starting point. But we're actually going to find it more useful to write it as a differential. So we're going to write that dW equals minus P dV. Now at this point here, we can't really go any further unless we know the relationship between the pressure and the volume right here, because this P right here, this is a function of volume, so you can't just simply do a straight integral of it. You can't treat it as a constant. This pressure here depends on the volume. But thankfully we know what the relationship is for an ideal gas. We know that PV equals nRT. And so if we rearrange for P, then we know that P equals nRT over V. And so now we can substitute what that is, what the P is. So we get that dW equals minus. So instead of P, we're going to write nRT over V dV. So that is what we're going to do. And now we can integrate this, because if we integrate both sides, if we find the integral dW is equal to, well, n number of moles, we're going to treat that as constant. So minus is obviously constant. So you can take that outside the integral. R is the gas constant, so clearly that's constant. And remember, we said it's an isothermal change, and so therefore T is constant in an isothermal change, so that can come out the integral. And so all you're integrating is 1 over V dV. Now, if you remember what the integral of that is, the integral of a 1 over x function with respect to x is just simply the log of x plus c. Don't forget the plus c. And so if we integrate both sides, then we're going to get that W is equal to minus nRT. And let's just give these limits just right here. So that we're going to go from V1 to V2. Then when we integrate, we're going to get log of V, the natural log of V, evaluated from V1 to V2. So we're going to just rewrite that, minus nRT, that's our pre-factor right here. And let's substitute in these limits. So we're going to get the log of V2 minus the log of V1. And now you remember your log laws, that the log of AB is equal to the log of A plus the log of B. This also works for subtraction and division. So what are we going to have here? Well, we're going to have minus nRT, but instead of two terms, we can simply combine these into one term. We can have V2 divided by V1. And you should also know that there is the power law of logarithms. So if you have ln of x to the n, this is exactly the same as n ln x right here. That's just how logs work. And so if we bring this minus here and bring that to the top right here, then that's just going to be a minus 1. And so what's V2 over V1 to the minus 1? Well, you're just going to flip the fraction over. So you get that the work done in an isothermal change is nRT ln V1 over V2. So that is how you derive what the work is in an isothermal change.